Hi everybody, Mr. King here. We're going to cover 6.4, chapter 6.4, exponential growth and decay in this lesson. We'll be looking at separable differential equations, which you're already somewhat familiar with or quite familiar with. And we'll look at solving some different examples. We will also look at a very important result that has relevance to the coronavirus crisis and mathematical modeling of epidemics, pandemics. And that will come from a very simple assumption that leads to a differential equation. And we'll work our way through some radioactivity, possibly, that is, in terms of the exponential function that goes with that, and possibly to Newton's law of cooling, which is another outgrowth directly related to what we'll look at today. So anyway, we're going to start out here with what is a separable differential equation? And what we have here with m of x plus n of y times dy dx equals 0 is a more general form of a separable differential equation. M of x is a continuous function of only x, and n of y, similarly, is a continuous function of only y. Of course, dy dx is the derivative of y with respect to x. Now, we know how to solve these already, but in this general form, here's what it's going to look like. We're going to move m of x. We're going to push it to the other side. And that will leave us with n of y dy dx is equal to negative m of x. And then to get the x's with the x's and the y's with the y's, we will move dx to the other side, and we will get n of y dy is equal to negative m of x dx, like that. And now we can see that we have the familiar form of the separable differential equation where we can use antiderivatives, or we can integrate on each side to move towards our solution of y as a function of x. Let's turn now to the example below. Find the general solution of this separable differential equation. The x squared plus 4, we can see here, is a function m of x, you might say, of x. And on the right side, well, it's written in a way where we don't see it quite the same way. But let's just go through this and you'll see that this is a separable differential equation. The first thing we're going to do is we're going to take this d of x and we're going to bring it to the other side. And so we're going to get this. We're going to have x squared plus 4 dy is equal to xy dx, like so. In the next step, we're going to divide by y. And we're also going to divide by x squared plus 4. Now, those of you know I don't always write this much work, but I want to be very clear here. These guys will go out. These guys will go out. And this leaves us with dy, little writing problem there, dy over y, a very familiar form. And then on the right side, we've got x over x squared plus 4 dx, like so. And now we see, yes, indeed, we have a separable differential equation here. And at this point, we can anti-differentiate, or we can integrate. I kind of prefer showing the integration here. Now, very quickly, we see on the left side, this is a very familiar form, and we see that we have the natural log of the absolute value of y for the integral of dy over y. Now, on the right, it turns out it's the same form. Well, why is that? So let's look at that. In the bottom, we have x squared plus 4. In the top, we have x. Now, the derivative of the bottom is 2x dx. Well, the differential, I should say. And so we're very close to that form here. So this is really a u sub, technically a u sub integration. And so we need a 2 here. And we need a 1/2 out front to undo. Those guys are reciprocals and they undo each other. And so at this point we can write what this derivative looks like. Excuse me, integral. Natural log of the absolute value of x squared plus 4. We need the 1/2 in front, of course, from that. And we're going to use C1 here. You'll see why in a few moments. Now, we can simplify this because we don't really need sticks. We don't need the absolute value on that x squared plus 4 because it's always greater than 0. It's non-negative. And so that's kind of nice. Next step we're going to do before we exponentiate is we're going to bring this 1/2, we're going to bring it up. So this is going to give us natural log absolute value of y is natural log of x squared plus 4, the 1/2 plus C1. Now you can move faster than this if you want. I'm being very careful here to show each step. Now x squared plus 4, the 1/2 is the square root of x squared plus 4 plus our C1 here, and here's our natural log of absolute value of y. Okay, we're getting very close here to our solution. I think you can see this developing. So when we exponentiate, that means we're going to raise e to the ln of absolute value of y and so forth. That's going to give us the absolute value of y. We don't need to show anything when we do that. And here we will get e to the ln of the square root plus C1. Now that technically is e to the natural log of the square root times e to the C1. And so I'm going to write it that way. So this is also very clear. And again, you don't have to show this. On the AP exam, they expect that you know how to do this. So now we have the absolute value of y. And e to the C1, we're just going to call that c. It's our constant. So e to the C1 is c. And then we've got the square root of x squared plus 4 right there. Now our final step here is to realize that it's the absolute value of y is equal to c times the square root. But we really want to have a solution for y. And because y could be positive or negative to equal this quantity here, we're going to say that y is equal to plus or minus c square root of x squared plus 4. Now, if we wanted to, we could say let k equal plus or minus c, and then that would lead us to the solution, the general solution here of a constant k times the square root of x squared plus 4, like that. And there's our solution. This is the general solution to the differential equation that we started with at the top, right here.